Okay, welcome to Robotics 2. In today's class, I'm going to talk about a couple of important concepts, and I would try to introduce these concepts in a very systematic fashion, and I will try to go slow. So if you have any questions, just raise your hand or ask the question or type the question in the chat window. So a quick review. I just want to tell you that uh, about 98% of the class did very well in project 2. So all the students were able to get the, the motion, uh, differential equation of motion integrated correctly, then add the sliders and have the Simulink code working. But recognize that code was implemented in Euler angles. Now, in today's class, first, I would like to talk about Quotonian implementation and then give you some idea on how to integrate quotonians and what are the issues with Quotonian integration, and then how do we overcome that and how can we perform this entire calculation in Quotonian. So here is the important objective. So as you can see on the screen, there are 12 equations of motion. So first 3 equations are associated with the velocities. So these are inertial velocities. These are body velocities. And we have a rotation transformation, which is nothing but yaw, pitch, and roll that converts body to inertial. So this rotation matrix is going to convert body to inertial. Now, next thing is what we have is we have Newton's law, summation of forces is equal to mass times acceleration. So this equation is summation of forces is equal to mass times acceleration. I take mass on one side, and now I have an equation for acceleration is equal to, that is given in terms of rotational rates and the linear velocities and the forces acting in x, y, and z direction. And at this point, I want you specifically to pay attention to these terms, fx, fy, and fz. In the next chapter, we would expand these terms. So right now, these terms are force in the x direction, force in the y direction, and force in the z direction. We will separate these forces out in terms of aerodynamic forces, gravity, and then we will actually expand these forces and use these forces in integration. Now, the next part is using PQR, which is nothing but the angular rates. These angular rates are in the body coordinate system. So these angular rates somehow need to be related to the inertial angular rates. And when we integrate inertial angular rates, what we get is inertial angles. The last equation is the moments, and we have the moment of inertias for the aircraft, and on the left hand side we have p dot, q dot, r dot, which is nothing but uh, angular accelerations. So these 12 equations were integrated numerically using Matlab with appropriate initial conditions, and then that led to the animation, and we saw that animation. And as you know, Jx, Jy, Jz, these are the moment of inertias, and then you used the moment of inertias corresponding to the Zagi airplane, and then it showed the simulation. Now, next thing what I want to talk about is, as we saw, the Euler angles become singular at 90 degrees. When the pitch is 90 degrees, you cannot distinguish between the roll and the yaw. So to overcome that, what we can do is we can use different implementations. And one common implementation of rotations is in quotonians. Now, when we have a quotonian, in the last class, we also talked about the quotonian. Quotonian has 4 elements. The first element can be thought as a scalar element, that is E0. E1, E2, E3 are the vector element. Quotonian is nothing but the axis angle representation of the orientation. And in today's lesson, I'm going to talk a little bit about how to perform the Quotonian integration and what to watch out for. Now, one thing I want you to understand, and I will emphasize this again, the quotonian that represents rotation is a unit quotonian, which means every time the absolute value of quotonian has to be equal to 1. So E0 square plus E1 square plus E2 square plus E3 square must be equal to 1. This is something similar to the unit vector that we look at when we study statics or dynamics. So every time we are performing any transformation, quotonian must be a unit quotonian. Now, we talked about this in last class. So we have an aircraft. Aircraft orientation can be represented as a yaw orientation change, followed by a pitch orientation change, followed by the roll orientation change. But what you can do is you can actually represent this entire sequence of transformation. And this is very important. You can represent the entire sequence of transformation as a quotonian. And I want you to understand this, very important. So quotonian Q can be represented as a sequence of transformation. And if you use Matlab, then the Matlab command to do that is EUL to QUAT. In the parentheses, you will have to specify yaw, roll, no, yaw, pitch, and roll. So what it means is you can represent this composite orientation change, which is initially yaw orientation, then pitch orientation change, and roll orientation change as a quotonian. And this quotonian will have 4 elements: Q0, Q1, Q2, and Q3. And I want you to understand that when we are going to differentiate a quotonian differential equation, these, the initial orientations, will form the initial condition to the differential equation. And when I show you the script, you will see what I mean by that. For an example, when we looked at project 2, when we performed the integration, we specified the initial orientation of the aircraft. So we specified initially the pitch is 0 degrees, roll is 0 degrees, yaw is 90 degrees. But when we are going to perform the integration in quotonian, what we need to do is we need to first convert that sequence of initial Euler angles to initial Quotonian and then use this Quotonian as an initial condition for the Quotonian integration. So this is something important. So if you are performing integration in Euler angles, your initial conditions will be in Euler angles. If you are performing integration in the Quotonians, your initial conditions must be in Quotonians. You cannot mix and match. You cannot supply Euler angle initial conditions for Quotonian integration. So with this information, let's look at how the Quotonian integration can be performed. So here is the easiest way. Say for an example, initially the aircraft had certain roll angle, certain pitch angle, and certain yaw angle. So let me give you an example. Initially the aircraft is 90 degrees yawing, 0 degrees pitching, and minus 90-degree rolling. These are the initial orientation. So this is the initial orientation. Before you do anything, step one is to get these values of psi, phi, and theta and find out these values E0, E1, E2, and E3. You can use the expression that is given here, or you can just use the Matlab command that will give you the Quotonian. The next step is looking at the representation of the rotation matrix. This rotation matrix is now expressed in terms of Quotonian. And please understand, E0, E1, so I just have to clearly mention this. Say you have a Quotonian. That Quotonian is derived or somehow represented by some roll, pitch, and yaw angle. So you have some yaw angle, some pitch angle, and some roll angle. This Quotonian has E0, E1, E2, and E3. These four elements. You can use these four elements to construct the rotation matrix as given over here. So you can construct a rotation matrix using the elements of the Quotonian, and if you were to compute this rotation matrix using the equation that we derived earlier, it will be exactly same as this rotation matrix. So that is something I want you to keep in mind. So again, this rotation matrix is used to transfer body angular velocities to inertial velocities, and these inertial velocities are integrated to find initial inertial distances. Now, the next important question is what happens when we are actually going to perform the integration. So please note, the first equation, which is the rotation matrix, you can use the expression that is given over here, or you can use the equation which is given over here. So you can use either this equation, I'm going to call this matrix 1, or you can use this matrix, this matrix 2. Both of them will give you identical answer. Second equation remains unchanged. The third equation changes. So earlier we just had roll rate, yaw rate, pitch rate, and roll rate. Yes, Q0, Q0, Q1, Q2, and Q3 is nothing but E0, E1, E2, and E3. Correct. Q0, Q1, Q2, and Q3 is nothing but E0, E1, E2, and E3. So now what I want you to do is, I want you to understand that this process of integration, how does this process of integration work? And what I'm going to do is, I am going to explain this in a slightly detailed fashion in next slide. But I want you to understand, when you are going to integrate, values of P, Q, R, remember PQR are the body roll rates. So P is the roll rate. P is the rate along x-axis. Uh, Q is the rate along y-axis, and R is the rate along z-axis. So you have P, Q, and R. So these are the angular rates. These angular rates, they come from next equation, which is given over here. So this equation, please note, this is the rotational dynamics equation. The rotational dynamics equation is going to give us the values of P, Q, and R at every time step. We are going to use these values of P, Q, R at every time step to integrate or to propagate the Quotonian from the initial Quotonian all the way to the end time. Now, when we are going to perform this integration, what's going to happen is, in almost all the cases, the Quotonian will norm of the Quotonian, or the absolute value of the Quotonian, will exceed 1. What it means is that Quotonian will no longer be unit Quotonian. If the Quotonian is not a unit Quotonian, that means it cannot represent the rotation. So to make sure that the Quotonian remains the unit Quotonian, there are two techniques. We actually use normalization, or we use something called as the cost function, and I will show you both these techniques. So what I want to do is, I want to spend some time on this equation. So this equation is represented in detail on this slide. So what I want you to do is, I want you to, for a second, imagine the expanded form of this equation. So what I want to do is, I want you to just see this. So this equation is going to look like E dot is equal to 0 multiplied by E naught minus P multiplied by E1 minus Q multiplied by E2 minus R multiplied by E3. Now, E naught is nothing but dE naught divided by dt. And if I'm going to perform the numerical integration, I can assume time step dt is equal to delta t, say is equal to 0.1 second. And then this equation can be written as dE naught is equal to 0.5 multiplied by minus P E1 minus Q E2 minus R E3 multiplied by 0.1. So what that means is, I want you to think about the numerical integration wherein you have the time on x-axis and value of E naught on y-axis. You start with some initial value of E naught. So E naught initial. And then what you do is, you actually have the timestamp, and you can actually keep on adding this small change. And that way you can actually find out the value of the subsequent E naught. In other words, what you can do is, this gives me the value of E naught at time t is equal to 0.1. So I have value of E naught, I have time t is equal to 0.1. Then I would use the value of E naught at time t is equal to 0.1 and propagate it, and then find out the value of E naught at time t is equal to 0.2. But it is not difficult to visualize that as we continue doing this across E0, E1, E2, and E3, thus the absolute value at each time instant will exceed 1. And to minimize, actually to make sure that it's a unit Quotonian, what we do is, we normalize that number. So which means, in every time step, in every propagation, After you get value of E naught, similarly, you are going to get the value of E1. Similarly, you are going to get the value of E2. And similarly, you are going to get the value of E3. You will normalize the resulting Quotonian. And that normalized Quotonian will be used as the initial condition for the second iteration. And this is very important concept. I just want to make sure that it is understood. And I will try to explain this once again, because believe it or not, uh, the field of inertial navigation does this all the time. So I want you to look at the expression E naught, E1 dot, E2 dot, E3 dot is 1/2 something like 0 minus P minus Q minus R, P 0 R minus Q, Q minus R 0 P, R Q minus P 0, and you have E0, E1, E2, and E3. So you have certain initial value. So you have at time t is equal to 0, you know the value of the left hand side. At time t is equal to 0, you know the value of rates. Maybe the rates are 0, or maybe the rates are non-zero. If your time step is known, say for an example, delta E naught, delta E1, delta E2, delta E3, and I'm going to have 1 divided by delta t is equal to this entire equation. I can take the delta t equation onto the right hand side. So what it happens is I will multiply this big expression by delta t, and your time step could be as small as 0.0001 second. Say it can be as large as 0.1 second. So if you have a large time step, your numerical integration is not going to be accurate. But if you have a small time step, your numerical integration can suffer from integration errors and floating point errors and round off errors. But then there are ways to compensate for that. So now for a second, I want you to understand that if I were to plot, if I were to have delta t on the x-axis, I have E0, E1, E2, and E3 on y-axis. So E0, E1, E2, and E3. So at time t is equal to 0, I start with these values. These are the initial values of Quotonian based on the initial Euler angles. But when I increment this by 0.1, so when I go from here to here, this is nothing but simple integration. So this is the integration. I'm assuming this to be a straight line, and I propagated, which means I found out the next value. So I found this value, this value, this value, and this value. Now at this stage, I have to make sure that modulus or absolute value of E is equal to 1. And most likely it won't be. And the reason for that is PQR are the rates. And these rates are in terms of, say, radians per second. So when you propagate these, your absolute value will never be equal to 1. So what you do is you say, hey, wait a second. You grab these values at this point. You observe that the norm of E, so I'm going to call this E01, E11, E21, and E31. You will say norm of E, or the absolute value of E, at this first step is not equal to 1. So what would I do? So what I would do is I will find out E01 square plus E11 square plus E21 square plus E31 square, and this is going to be greater than 1. This is going to be greater than 1. I will find out the square root of this absolute value, and I'm going to call this norm of E1 or absolute value of E1. And I would divide, before I go to the next time step, I will divide each element E01, E11, E21, E31 by this absolute value. What would it do is it would, just like making it a unit vector, it will normalize the Quotonian. So this is something that you should keep in mind when you are trying to propagate the Quotonian. Now, there are two ways to achieve this. So if you are going to use Matlab using some sort of a Range Katta method, so in every iteration, whenever you get the values, before you pass these values for the next iteration, you perform the normalization. And we will talk about it in the actual implementation. The second way to do this is adding some sort of cost function. And I will not discuss in lot detail what this cost function does, but this is sort of a penalty function, wherein what the purpose of this penalty function is, it will constrain the values of E0, E1, E2, and E3 at every step to be equal to the 1. So what it means from implementation point of view, rather than integrating the equation which with zeros at the diagonal element, you would have a large value of lambda, which could be something like 1000 multiplied by 1 minus the absolute value. So what it's going to do is, it at every time step, every iteration, it's going to use this constraint to find out the values of E0, E1, E2, and E3 at that time step. So you have this constraint equation, and this constraint equation will make sure that your differential equation uh, for Quotonian is normalized at every time step. So please keep this in mind. This is a very neat trick that is used when we look at inertial navigation. The next part is Range Katta integration, and we talked about this, but now what I want to do is I want to go to the Matlab and show you how this integration is done. But I just want to tell you, what we will talk about today is not the complete solution of the problem, but a partial solution of the problem, because we can propagate the Quotonian, but when we have to finally compute the answer, you can't just visualize a Quotonian. You will have to convert that into Euler angles so we can represent the rotation in 3 dimensions. So I'm going to show you the Matlab script. But before I go to Matlab, any questions on this integration? So what we are trying to do, we are trying to write the code to perform the Quotonian based integration. Okay, now on the physical UAV, what happens is, typically what you have is, you have something called as inertial measurement unit. So what you have is something called as IMU, and this IMU is going to give you values of P, Q, and R. So but please note that PQR are nothing but the body rates, and you have an IMU in your Apple phone or Android phone, and you can actually look at the orientation of your phone So if you look at an app, so you will see an IMU app in Play Store or in Apple Store, and that would show you the orientation, the angular rates of your IMU. So basically, your phone has an IMU which has 3-axis gyroscope, 3-axis accelerometer, and 3-axis compass. So in actual UAV, you no, dot over PQ are the angular accelerations. So P dot, Q dot, R dot are angular accelerations. So quick recap, if you look at the equations, these, once again, these come from the equation T is equal to I alpha type. So you have alphas here, and this equation comes from F is equal to MA. So U dot, V dot, and W dot are nothing but accelerations, and P dot, Q dot, and R dot are angular accelerations. Does that answer your question, Zubir? Okay, so PQR are the angular rates. To answer Borna's question completely, please understand the gyros, accelerometers, and compass, they are noisy. So you're not going to get a very clean measurement. You're going to get a measurement something like this. So what we do is we use filters, and we'll talk about low pass and high pass filters. And then what we do is something known as sensor fusion. So in sensor fusion, we combine the information coming from gyro along with information coming from accelerometer, along with the information coming from compass to come up with the best possible estimate of roll, pitch, and yaw angles. And again, sometimes the positions. Sometimes if you have GPS available, the smartphone app can fuse the data or combine the data from the GPS and the IMU and give you a better estimate. Okay, now what I'm going to do is I'm going to go to Matlab, and I will share my entire screen. That way you will be able to see. So now you should be able to see my entire screen. Okay, are you able to see my entire screen? So what I'm going to do is I am going to, I need to make sure that I am able to see my chat window as well. Okay, so now you should see my screen, the chat window. And first and foremost, I'm going to go back to the two functions that we used in the very beginning. So we used a function called derivative underscore run dot m, and the second function that we used, that is derivatives dot m. What I'm going to do is I'm going to copy and paste this function into chat window. What I want you to do is I want you to save this function along with the derivative underscore run in a separate folder, because I don't want this function Matlab to get confused between this function with another function that may be in the memory. So what I'm going to do is I'm going to copy this function and I'm going to paste this in let me see. Yeah, it's not going to let me copy the whole thing. I'll copy it partially. So first, copy. Please note this function is for the MAV with unity parameters. So all the parameters for this UAV are unity. Okay, actually the last part did not come through. So I'm gonna paste the rotational kinematics copy. Okay, so here is what I want you to do. First, I want you to construct a Matlab M file with line from 1 to 33, then append line 36 to 66, and then finally append 67 to 70. Then I'm gonna give you this derivative run function. Okay, I'll give you the whole function and tell you what would happen. So this is the whole function. Now I want you to save derivatives underscore run function and this derivatives underscore m function in one folder. Add that folder in your Matlab path and then run derivatives underscore run. Now what I'm going to do is I'm going to do derivatives underscore run, and all of a sudden you will have these three plots. I just want to make sure that you are able to get these three plots. You will have figure 2, you have figure 3, and you have figure 4. I just want to make sure that you are able to get these three plots, and there will be an empty figure 1. Everybody got that? So what I want you to understand is that figure 2 is plotting the first 3 elements of the solution. Figure 3 is plotting the next 3 elements of the solution. And figure 4 is plotting the last 4 elements of the solution. And I want you to quickly look at what these elements are. So if you look at the derivatives.m, the states are Pn all the way to you are up to R. So there are 13 states, and this E0 is state 7, E1 is state 8, E2 is state 9, and E3 is state 10. So these 4 states, which is nothing but the propagation of Quotonian, is plotted in this figure. So as you can see, is you have this Quotonian. That is how the Quotonian is propagated. Now what I'm going to do is I am going to go line by line from in this code. But before I do that, I just want to make sure that everyone got the same answers. So this code is actually implementing the equation that we talked about, which are in terms of Quotonian. Couple of important things that I want to point out. First and foremost, look at the position kinematics expression. Position kinematics expression does not contain roll, pitch, or yaw. It contains E0, E1, E2, E0, E1, E2, and E3. So position kinematics equation does not have roll, pitch, and yaw angles. If you look at the rotational kinematics equation, also does not have roll, pitch, and yaw angles. So what this entire expression is, this entire expression is implemented in Quotonians. Everyone understood this, that this entire expression for position kinematics and rotational kinematics is implemented in Quotonian. So if we want to solve this expression, we cannot supply Euler angles. We cannot say roll value, pitch value, and yaw value as initial condition. So what I'm going to do is, let's go back for a second to the derivatives underscore run dot m. If you compare this derivative underscore run dot m file with the previous version, wherein we had roll, pitch, and yaw angles, please note the initial conditions contained initial value of roll, initial value of pitch, and initial value of yaw. Now, if you look at the derivatives underscore run dot m file, please note, first we specify the time span, then we specify the initial yaw value. So the initial yaw angle is 0. This is the initial yaw. Then theta value, this is the initial pitch value. And phi0 is the initial roll value. And the next step is important. Since we are performing the Quotonian integration, we need to take these initial yaw, pitch, and roll values and convert that into the initial Quotonian. So I use the command EUL to QUAT. This will convert Euler angles to Quotonians. And please note, by default, this is Z, X, and Z, Y, and X. So this is Z, this is Y, this is X. So this Euler angle to Quotonian rotation, it completely depends upon the sequence of Euler angles. There are 12 Euler angle sequences, but for our purposes and in robotics, we use yaw angle first, pitch angle second, and roll angle third. So yaw is about the Z axis, that's why Z. Pitch is about Y axis, that's why it's Y. And phi is about X axis. So this rotation sequence is Z, Y, X. And now what you do is you have value of Q. This is nothing but E0, E1, E2, and E3. And I'm supplying these values over here. So this is nothing but the Quotonian, the initial Quotonian is passed on. Everyone understood this? Okay, correct. If that is what the error you are getting, robotic system toolbox is included free of cost in your Matlab. So what you need to do is you need to go to home, click on add-on, and then click on get add-on, and then get robotic system toolbox, and it will be installed immediately for the Matlab. So EUL to QUAT, if it is not running, that means you may not have the robotic system toolbox installed. So for that, again, you need to go to home, you need to go to add-on, you need to get add-on, And then once you click there, it will take you to this add-on explorer. And then there you would have the list of toolboxes that are installed and the other toolboxes that you can install. So here you can go and look for robotics system toolbox. So here, click on robotics. Robotic system toolbox. And then you can download this robotic system toolbox. As you will notice that I have installed all these toolboxes, so I do not have that problem. Does that answer your question, Jade? Okay. Now, what I'm going to do is I'm going to go line by line through this code. Now, please note, and I would recommend that you compare this derivatives code with the derivatives code that you probably used in your project or the derivatives code that I shared earlier. So you will notice that in this derivatives code, again, I have t as an independent variable, states, and then I have f state. These are the forces. So these states are the initial values. So I have Pn, Pe, oh, this is Pd, Pn, Pe, Pd. Please make this correction, Pn, Pe, Pd. Line number 4 is Pd. And then I have U, V, W, E0, E1, E2, E3. So please note that earlier I had roll, pitch, and yaw, but now I have the quotonians as these states. So I have quotonians as these states. Then I have PQR just as before, and then I have Fx, Fy, Fz, the torque or the moment about x-axis, moment about y-axis, and moment about z-axis. Now, if you go down from line 22 to line 33, I'm saying all my UAV parameters are equal to 1. And if you are going to simulate for the Zagi airplane, your parameters will be different as you worked out in project 2. Now, I want you to specifically look at the position kinematics. And in position kinematics, as I discussed earlier, that there is no roll, pitch, or yaw. There is just Quotonian, elements of the Quotonian that we constructed, state 8 from 7 to 10. So these are the elements of Quotonian. That's what we have. Then next position dynamics is I have the rates and I have the external forces. For this particular application, the external forces are 0. The next part is what I want to show you is the rotational kinematics equation without normalization that I just talked about. So if you look at the textbook or if you look at the slide that I showed a moment ago, this is the rotational kinematics equation, which is commented without normalization. But I want to look at the second set of equation where the rotational kinematic equation is normalized. So you can see here the value of lambda is 1000 and factor is nothing but the factor lambda multiplied by, in the parentheses, 1 minus the norm of the Quotonian. So the norm of the Quotonian is nothing but 1 minus E0 dot square plus E1 dot square plus E2 dot square plus E3 dot square, which means all the elements that we get here from line number 8 to line number 11, they are individually squared. So this is element by element square operation. That's why there is a dot. So we dot and square, so elements are squared, and then I subtract those from 1 and multiply with this large value, which is 1000. And now I want you to look at the equation from 56 to 59. From equation 56 to 59 is just similar to equation 47 to 50, but you have this factor multiplying E naught, factor multiplied by E1, factor multiplied by E2, factor multiplied by E3 at the diagonal element. So this expression is the expanded version of the expression that I showed a minute ago with the cost function. And what I'm going to do is I'm going to just let you think it through for a second. And I want you to verify that this equation that you see in front of you is the same equation that we discussed a minute ago, wherein you have a cost function at the diagonal, and that cost function is actually normalizing the Quotonian every time. Now, what I want to tell you is this integration is performed in an ideal situation. So it may happen that even if you don't normalize, the Quotonian that you get could be a unit Quotonian. What I'm trying to say here is if you comment this and uncomment this, right click, uncomment, go back to editor, save, and go back to derivatives underscore run and click on run, you may get good results. But these results are not guaranteed because we are not ensuring that at every time step, the Quotonian that we obtain is the unit Quotonian. And what would most likely happen is if you had noisy sensor measurements, or if you have external forces, you can actually plot the norm of the Quotonian at every time step. And you will notice that the norm of the Quotonian may exceed 1, which means it won't be a pure rotation. Okay, I'll show you. Go back to derivatives. Now, can you see that there are equations, rotational kinematics with normalization? That is what we used earlier. Now, I selected all this and right click, and then you have comment. I commented that. Then I went back, highlighted these equations, right click, and uncomment that. So which means now I'm using the rotational kinematics equations without normalization. And then save and then run. And then you will get similar plots. And even though in this particular case, this is just the ideal integration, so that's why we don't see normalization playing a big role. But I would strongly recommend that you normalize your Quotonian at every step. Now, the next natural extension of the discussion is, some of you may say, hey, wow, that is fantastic. Now let's take this information. Line 31 and 32 repeated. Okay, let me see. Where line 31, 32? Here? No, not here. 31. Borna, I don't understand your question. Which line 31 and 32 are we talking about? This? No, line 31 is line 31. MAV gamma 1. Yeah, okay. If there are two MAV gamma 1s, take one of the MAV gamma 1s out. Yeah, so yeah, just take this out. Should work. Let's try. Works. Same with 4, does not change anything. Now, I don't know what 4 are we talking about, John? Gamma 4. Okay, there are two gamma 4s. Ah, okay. Yeah. Okay. So, but I would encourage you to do this with your Zagi plane. So, okay, before let me finish this discussion quickly. Any other questions related to code? So what I want to do is I want to show you something very interesting. Check this out. Now the last 4 lines, which is I is equal to 1 to m, draw aircraft, all that stuff, it's actually plotting the aircraft. And what I want to do is I want to uncomment this. So please understand, I'm going to uncomment this. I'm going to uncomment this. And let me ask you this question. And you can answer in the chat window. If I run this code now, would it plot the aircraft? If I run this code now, would it plot the aircraft? You can tell me before trying it. It won't. The reason for that is the values of the output, the Y values that we are trying to do, they are in quotonians. And the values that this guy is expecting, they are in Euler angles. So there are two things that we could do. First of all, we can take the quotonian that we obtain. So what we do is we take the y's here, y's of 1, 7 to 10, and convert that instantaneous quotonian. So let me tell you this. And I want you to try this, otherwise I will solve this in next class. So convert quotonian in Euler angles at every time step. And why do we need to convert the quotonian into Euler angle? Because our 3D animation, the animation is in 3 dimensions. Quotonian is a 4-dimensional concept. You cannot show 4 dimension in 3 dimensions. So you will have to convert the quotonian into Euler angles and construct a new vector, which I'm going to call y new, which consists of all these values. So for an example, y values from here to here, then you will have comma, then you will have y 4 to 6, comma, and you will have 7 to 10, which you will convert from quad to ul, and then you will have to supply y 4 to 6, and then you will have to append last elements, which are y all rows 10 to 13. And then you can send this to draw aircraft and it will draw the aircraft. So this is one way of doing it. Second way of doing it, and I will talk about it maybe later, is what you can do is you can use the quotonian itself to perform the mapping. What it means is, let me go back to my code for a second. So solution 2. So if you go to draw aircraft.m, look at the rotation matrix that we are getting. Our rotation matrix here is constructed in terms of Euler angles. What I would do is I would take the values of E0, E1, E2, and E3 at every time instant. Please note, we have that data. 1, 2, 3, 4, 5, 6, 7. This is the Quotonian. This is the Quotonian. This is the Quotonian. I would take these values of Quotonian and construct the rotation matrix that is given here. And then I can perform the same animation. So there are two ways to perform the animation. You can, since Quotonian is a 4-dimensional concept, but our animation is in 3 dimensions, we somehow need to convert that 4-dimensional information in 3 dimensions for plotting. That can be done either at the derivatives run level, or that can be done at the draw aircraft level. Everyone understood? And again, this is not an assignment, but I would encourage you to do this because that will make your understanding of Quotonian and Quotonian computation clear. Okay, before I go any further, any questions? Quad to Euler is for 7 to 10. Quad to Euler, yeah, quad to Euler, you're right, it's for 7 to 10. And I think this is 11 to 13. 11 to 13. Line 23. This code is not correct. So this code is not correct, but if you still want it, you're welcome to take it and play with it and make it work. Yeah, the figure 1 didn't show anything because there was no aircraft drawn. Figure 1 will be populated if the animation draws an aircraft. That's why you see there is figure 2, figure 3, figure 4, and figure 1 is for drawing animation. Okay, any questions? There is something important that I would like to discuss. So again, it's not a homework, but it's just an assignment, sort of a self-learning assignment. Try to make your animation draw aircraft work with the Quotonian implementation. Because in Matlab, once you get this working in Quotonian implementation in Matlab, Simulink is straightforward. Now what I want to do is, I want to talk about S functions. And for that, I want you to go to my ASU. I want you to go to my ASU. Go to Canvas. And I'm going to take you to Canvas, my Canvas. And then I want you to go to Module. Canvas. And go to Module. And in Module, I want you to go to Matlab codes. Everyone, please pay attention. Go to Matlab codes. Go to Matlab codes. And there is something called as sfunction.rar. Please download and extract this folder. Everyone, please download sfunction.rar and extract it on your desktop. So any questions? everyone is able to extract s function.rar onto the desktop. This s function.rar is on the canvas modules under Matlab codes. Now what I want you to do is, I want you to open that s function and you will notice s function dot rar, when you expand, will have a second order underscore m.m, second order ODE MDL, and it will have the debug info. So what I want you to do is, I want you to first open second order ODE.mdl. Open second order ODE.mdl. Then I want you to open second order underscore m. So now you should have two files in front of you. You should have two files. One is the Simulink block, and the other one is the Matlab code. I just want to make sure everyone has this. Okay. Everyone has the Simulink file and the Matlab file. Okay, now I want you to listen to this discussion very, very carefully. So Simulink has capability of taking an M function and convert it into something called as S function, where S function stands for Simulink function. The Simulink function could be a level 1 function, could be a level 2 function. So the purpose of the Simulink function, this is like a wrapper. So what it does, you can have a code written in Fortran. You could have a code written in C. You could have a code written in some other language. But what you can do is, you can call this code. You can call this code. You can wrap this code around. You can have a Simulink wrapper that you can wrap around this code and still run this code inside the Simulink environment. This is pretty powerful. Just imagine that you have a C code, and that C code is written for Arduino. So you want a certain algorithm to be implemented on an embedded system like Arduino, and you have a C code. But what you want to do is, you want to use the exact same C code inside the Matlab environment to see if there are any issues with that C code. And if you want to check the data, tap into the data, inspect the data, plot the data, you won't be able to do that with an Arduino. So what you can do is, you can take the C code, wrap it inside the S function, and run inside the Matlab environment. So if you double click on second order underscore M, this will open as S function level.m. Now this S function name, second order underscore M, is same as the name of this function. This is same as the name of this function. S function can take some parameters. So what I have here is, there are two parameters, and this example directly comes from the example in Appendix D. And I need to write this down. This example, Appendix D. So wherein what you have is, you have a simple spring mass damper system. So check this out. You have a spring mass damper system that we studied in lot detail in Robotics 1. So what I did is, I converted that spring mass damper system as a first order equation system. Now you may see that this function that you see here has the derivative on the left hand side and the states on the right hand side. This is exactly same as derivatives.m function, where you have the derivatives Pn dot on the left hand side and the states on the right hand side. So I want you to see this. You have x dot MDL derivatives, and these are the inputs. Now I want you to see that this function is same, it has same structure as derivatives dot m. So this is where the differential equation goes. This is where the differential equation goes. Next, you have this function. This is nothing but the output, which means you have the states that are coming out. And what I'm saying is the output is state 2 multiplied by a constant. So this is the output of the function. This is exactly same. This is exactly same as x dot. This is exactly same as x dot. This is nothing but the output of the function. So what you have is here, you have the states. Now please note that this code needs to be wrapped around the Simulink wrapper. And this Simulink wrapper has a very specific structure. And the reason it has a specific structure, because then you can wrap C function, you can wrap Fortran function, you can wrap some other, maybe Python function. So what you have is, if you look at this wrapper, the structure of the wrapper will never change. It will always have function, sys, x0, str, ts. So these variables are going to remain the same. This is the name of the function. This is the name of the function that will have the first input as time, the second input as states, third input again as the states. Then you would have a flag, then you will have parameters. So you are going to have states and parameters that are supplied. And this structure remains the same. This never changes. So from line 1 to line 12, it's going to be the same, except this function will have different name. And these parameters could be different. Now, what you need to do is you will have to initialize. So this initialization means supplying the initial values of x0 and the system and the time, and this will always be called MDL initialize size. And why it is called MDL initialize sizes? Because this is something that Simulink calls. And then you will always have sizes is equal to sim sizes. Then you will have to supply the number of constant states. So in this particular differential equation, I have two states, x1 and x2. So number of constant states are 2. In this differential equation, I just have one output. That's why the number of outputs is 1. Now, and basically you will have number of inputs. So that you will have to supply, and then you will have to supply the sample time. So it says just one sample time. You will supply the initial conditions. Then str is always going to be an empty matrix, and you will supply the continuous time. This is the initialization function. Then you will actually have your derivative function. So you can actually grab your derivatives.m and place it over here and make the appropriate changes from line 24 to line 29 to make it work. Now, the next part, I will answer your questions, Zubir, in just a second. So, and the last part is you have this output. Now, what you can do is go to Simulink, and what I have done is I have this differential equation, and I'm supplying a square wave. You can change this square wave to sine waves to sawtooth wave or something like that, and then run this code, and then you will see the input and the output. Notice output is given as the blue line, and the input is given by yellow line. Output is lagging because system has some damping. If you go back to this and then change the value of damping as 0, if you change the value of damping as 0, and if you run, now observe that there is no lag. there is no lag, but the reconstruction is not super duper accurate. And you can change that by manipulating the simulation parameters. Now, to answer Zubir's question, in this particular case, we used a function that was defined inside the Matlab environment. So you can use, you may say using S function is sort of an overkill. I can just use an interpreted Matlab function. That's totally fine. But the power of S function is if you have a C code, you cannot use an interpreted Matlab function to run the C code inside the Simulink environment. So with S function, you can actually take the C code or maybe Fortran code and run. So if you go to library browser, and I would encourage you to play with this. I want you to go to the library browser. And once the library browser opens, you can go to user-defined functions. In user-defined functions, there are S functions, and there is sort of a tutorial on different types of S functions. So go to user-defined functions, and then go to S function examples. Double-click S function examples. And please note, this is the power of Simulink. You can have an S function that can be written in Matlab. You can have an S function that can be written in C. You can have an S function that is written in C++, or you can have an S function that is written in Fortran. So you can have your native C code, C++ code, or Fortran code that can be implemented inside the Simulink environment. So I'm going to stop here, but I would be happy to answer any questions that you may have.